A world without maps once existed, and its secrets were unlocked using only shadows and stars. This is the story of the lost art of measuring Earth before modern science, a tale of human genius that shaped our world. By the end, you will understand how ancient thinkers calculated our planet's size with stunning accuracy, using little more than a stick and some clever reasoning. We will uncover how a single well's shadow revealed the Earth's circumference, and how sailors navigated vast oceans guided only by the night sky. What part of our modern world would you try to measure if you only had the sun and your own wits? A farmer's footsteps across a field, a sailor's gaze tracking the sun from dawn to dusk. These were the first, most fundamental units of measurement our ancestors ever knew. Long before rulers and tape measures, the human body itself was the ultimate tool. A cubit was the length of a forearm, from the elbow to the tip of the middle finger. A foot was quite simply a foot. These were intuitive, always available measures that allowed for the division of land, the building of shelters, and the fair trade of goods. But as small villages blossomed into great cities, this personal scale was no longer enough. The world was growing larger, and our methods for understanding it had to grow as well. Consider the ancient Egyptians, whose entire civilization was defined by the rhythmic flooding of the Nile. Each year, the river would swell, wiping away the boundary markers between fields. To restore order and fairness, surveyors used long, knotted ropes to precisely re-measure the land, a practical necessity that gave birth to the science of geometry, a word which literally means earth measurement. Over in Mesopotamia, scribes pressed styluses into wet clay to create the world's first known maps, charting fields and cities with an astonishing attention to detail. These were not merely administrative tasks, they were profound acts of imposing human order onto the natural world, a declaration that our environment could be understood, quantified, and mastered. Can you imagine trying to navigate your daily commute using only the span of your hand or the number of days a journey took? This foundational drive to measure, born from sheer necessity, would soon lead our ancestors to look upward, from the soil at their feet to the vast, predictable clockwork of the heavens above. A Phoenician trader, alone on the dark sea, had only one fixed point in the spinning sky, the North Star. For him and for countless navigators across millennia, this star was a promise of direction, an unwavering guide that never dipped below the horizon. The heavens were a living map, and sailors learned to read its patterns with an intimacy we can scarcely grasp today. Polynesian voyagers, crossing the vast emptiness of the Pacific, memorized the star paths, knowing that each island chain lay beneath its own celestial signpost. They understood the subtle swells of the ocean, the flight patterns of birds, but the stars provided the ultimate roadmap, passed down through chants and stories. The Vikings, too, navigated their longships across the North Atlantic using a sunstone and their deep knowledge of the sky, a knowledge so precise it was a form of magic to the uninitiated. This was not just navigation, it was a conversation with the cosmos. The Greeks later gave this art a mathematical backbone with tools like the astrolabe, a device that could measure the angle of a star above the horizon, translating celestial position into terrestrial location. The sky was more than a tool, it was a divine script where myths of heroes and beasts were woven into the practical science of finding one's way. What ancient journeys are still written in the light of those same stars we see tonight? This profound celestial wisdom found its perfect partner in the relentless, predictable journey of the sun. That same sun, a dependable clock in the sky for farmers and sailors, held a deeper secret for those who knew how to look. In the great library of Alexandria, a scholar named Eratosthenes noticed something peculiar about a local well. At noon on the longest day of the year, the sun shone directly down into its depths, casting no shadow. Yet he learned that in the city of Scene, far to the south, a vertical stick cast a slight shadow at that exact same moment. This observation was the spark of a revolutionary idea. Eratosthenes realized that if the sun's rays were arriving at different angles in two different places, the Earth itself must be curved. He did not need complex instruments, just a keen mind, a measuring stick, and the patience to track a shadow. By calculating the difference in the shadow angles and knowing the distance between the two cities, he performed a feat of logic that still inspires awe. He geometrically extrapolated the entire circumference of our planet, arriving at a figure within a few % of the value we know today. This was not magic. It was the power of pure reason applied to a simple, everyday phenomenon. Sundials and shadow sticks were more than just timekeepers. They were the first scientific instruments for measuring space itself. Babylonian and Chinese astronomers refined this art, creating elaborate sundials that tracked the sun's shifting path through the seasons. These devices informed everything from the planting of crops to the planning of empires, turning the sun's daily journey into a tool for human progress. What grand truths about our universe might be hiding in the simple patterns we overlook every day? This elegant solar logic was just the beginning, setting the stage for thinkers who would use pure geometry to map the cosmos from the ground up. The summer solstice in Scene presented a perfect vertical line of light, a beam of sunshine touching the very bottom of a deep well. Eratosthenes understood this was not just a local curiosity, but a key to a global truth. He realized that if the sun was directly overhead in one city, yet cast a measurable shadow in another, the only logical explanation was a curved surface. His genius lay in transforming this simple observation into a planetary measurement. He hired a man to pace the distance between Scene and Alexandria, establishing a baseline of roughly 500 miles. Back in his library, he measured the shadow cast by a vertical stick in Alexandria at that same solstice noon. The angle was just over 7 degrees, a fraction of a full circle's 360. With elegant geometry, he reasoned that if 7 degrees separated these two cities, then the full circumference of the Earth must be 50 times that distance. His final calculation was a number so vast it must have seemed almost mythical, and yet it was within a slender margin of our modern value. He achieved this with no satellites, no lasers, only the parallel rays of the sun, the logic of a sphere, and the profound power of a questioning mind. His work stands as a monument to the interdisciplinary spirit of the ancient world, where a poet and librarian could, through geography and geometry, measure the entire world. What profound truths are waiting for us to uncover, not with new technology, but with a new way of seeing what is already before us? This groundbreaking achievement did not exist in a vacuum, but spurred a new era of land-based exploration and mapping. From the sprawling fields of the Roman Empire, a new kind of order was being etched into the landscape. Surveyors known as agrimensors worked with heavy chains and simple sighting instruments, dividing the land into precise grids. Their challenge was a constant one: how to measure what you cannot directly reach, like the width of a river or the height of a distant hill. Their elegant solution was triangulation, a method rooted in the unchanging truths of geometry. By establishing one carefully measured baseline and then sighting the angles to a distant point from each end, they could use the properties of triangles to calculate any distance with remarkable accuracy. This was not just about drawing lines on the ground. It was about creating an invisible web of mathematical relationships that could map an entire empire. The Greek Dioptra, an early theodolite, perfected this art, allowing for the meticulous charting of coastlines and mountain ranges from a handful of key vantage points. Can you see the invisible triangles stretching across the countryside, turning the chaotic terrain into a solvable puzzle? This geometric logic was the engine behind the Roman road network, enabling engineers to plot the straightest, most efficient paths across continents, binding the empire together with routes calculated by angle and line. The detailed land registries they created ensured fair taxation and settled property disputes, proving that a map was not just a picture, but a tool of governance and peace. Centuries later, this same principle would be scaled to its absolute limit during the Great Trigonometric Survey of India, a monumental effort that spanned decades. Teams of surveyors endured immense hardship, slowly marching northward, measuring a chain of triangles that would eventually climb the Himalayas themselves. The principles they used, however, were fundamentally the same as those of the Roman surveyor with his chain. Every time your phone's map instantly pinpoints your location, it is relying on a modern form of this ancient art, using signals from satellites to perform a kind of celestial triangulation. This profound connection between past and present reveals a timeless truth that the human drive to chart our world transforms the tools we use, but the underlying geometry remains constant. As these geometric webs spread across the continents, a parallel revolution was taking place on the open ocean, where sailors faced the ultimate challenge of navigating a featureless blue plain. Out on the open ocean, where the horizon is an unbroken circle, ancient navigators developed a sixth sense for the sea itself. They could feel the subtle shifts in ocean swells as they reflected off distant, unseen islands, and they understood the language of bird flight, knowing that certain species would only fly out so far from land. For the Polynesian voyagers crossing the vast Pacific, this knowledge was a living map, an oral tradition chanted from one generation to the next, allowing them to find specks of land in an immense blue wilderness. This art of wayfinding was paired with a practical technique used by sailors across the globe, dead reckoning. A sailor would throw a log overboard, attached to a rope with knots tied at regular intervals. By counting how many knots slipped through his hands in a set time, he could estimate the ship's speed. He would then mark his estimated new position on a chart, a best guess based on the direction sailed and the distance traveled. This method was fraught with uncertainty, as currents and winds could push a ship far off course without the crew even realizing it. The invention of the magnetic compass in China was a revolution, giving sailors a constant, reliable reference to the north that worked even under cloudy skies. And when land was near, the simple lead line, a weighted rope marked with depths, told them not only how deep the water was but, by the sediment stuck to the tallow on its end, what the seabed was made of, a crucial clue to their location. It was with these rudimentary tools that the Vikings dared to cross the stormy North Atlantic, their journeys a testament to incredible courage and adaptability. What must it have felt like to sail for weeks into an unknown expanse, your entire world confined to the wooden deck of a longship, trusting in the stars, the swell, and a flickering magnetic needle? This hard-won maritime prowess did more than just conquer oceans. It wove the first fragile threads between continents, setting the stage for a world that was slowly, bravely becoming connected. In the quiet of his observatory, a scholar in Baghdad turns a beautifully engraved brass disc. His astrolabe is more than a tool. It is a miniature universe held in the palm of his hand. This device, and its simpler wooden relative, the quadrant, transformed the abstract movements of the heavens into tangible, measurable data. The astrolabe was a star chart, a clock, and a navigational aid all in one. Its rotating plates, etched with the patterns of specific latitudes, and its intricate web of pointers allowed a user to solve problems of time and space with a simple twist of the wrist. It could tell the hour from the sun by day or a star by night, determine the direction of Mecca for prayer, and even forecast the positions of celestial bodies. This was a portable computer, its logic encoded not in silicon but in brass and careful craftsmanship. Across the Islamic world and later in medieval Europe, these instruments became essential for astronomers, merchants, and explorers. They democratized celestial knowledge, taking it from the realm of pure theory and placing it into the hands of anyone willing to learn its use. The Persian scholar Al-Biruni took this precision a step further. Using a massive quadrant to measure the angle of the horizon from a mountaintop, he calculated the Earth's radius with an accuracy that would not be surpassed for centuries, refining the ancient method of Eratosthenes with stunning new detail. The quadrant, a quarter circle of wood or metal with a weighted plumb line, offered a more direct, if less versatile, way to measure a star's height above the horizon. Its simple scale gave sailors and surveyors the power to find their latitude on the open sea or in an uncharted desert. In an age before digital screens, these devices represented a perfect fusion of artistic beauty and mathematical function. Their engraved scales were works of art, yet every line served a precise computational purpose. Is there a lesson for our own technology in this elegant marriage of form and function, where the tool itself teaches the user about the cosmos it represents? These intricate devices marked a high point of hands-on celestial measurement, yet even as they were being perfected, a quieter revolution in recording and replicating knowledge was taking place in the scriptoriums of monasteries and the workshops of early printers. Yet while instruments charted the stars, the human imagination was mapping a far more wondrous universe. In the icy realms of Norse belief, our world was not a sphere but a great flat disk called Midgard, encircled by the vast body of the serpent Jormungandr. This was a cosmos where geography was divine drama, where the very dimensions of the earth were defined by mythic beings. The Greeks told of the Titan Atlas, condemned to hold up the celestial sphere, a story that gave tangible form to the immense gap between earth and sky. In the Vedic traditions of ancient India, the entire universe was often envisioned as a cosmic egg, containing all of space and time within its shell. These were not mere fables, but profound frameworks for understanding a world without scientific data. They answered fundamental questions of scale and boundary, transforming the terrifying emptiness beyond the horizon into a structured, meaningful narrative. Consider the intricate songlines of Aboriginal Australians, epic dreamtime stories that wove together creation, morality, and a practical guide to the land. A single song could describe the features, resources, and navigation routes across hundreds of miles, encoding a living map within a sacred melody. To travel was to sing the land into being, step by step. These mythological cosmologies did more than just explain the world, they made it manageable. They provided a moral and spiritual context for the vast unknown, turning a daunting journey into a pilgrimage and a distant mountain into the throne of a god. Every culture's conception of space was, therefore, a form of measurement, a way of placing human life within a grand, sacred order. What does this deep-seated need to clothe the cosmos in story reveal about our own place within it? This symbolic mapping of existence, rich with meaning, would slowly be challenged by a new insistence on observable, repeatable proof. The stones of the Great Pyramid of Giza were laid with a precision that still defies easy explanation. Its base is nearly a perfect square, its sides aligned with the cardinal directions with an error of less than a fraction of a degree. This was not merely skilled construction, it was a form of worship written in stone. The builders encoded mathematical constants like the golden ratio into its very proportions, a ratio believed to represent divine harmony and aesthetic perfection. They designed the narrow shafts within the pyramid to point directly at specific stars, threading celestial pathways through millions of tons of rock. This was sacred geometry in its purest form, the conviction that by replicating the perfect ratios of the cosmos here on Earth, one could build a bridge to the gods themselves. This profound belief resonated across the ancient world. At Stonehenge, the great trilithons frame the rising sun on the summer solstice, turning the monument into a massive astronomical calendar. Hindu temple design was governed by intricate mandalas and geometric formulas, with every dimension calculated to channel spiritual energy and mirror the structure of the universe. The Mayans built their pyramids as sacred mountains, with stairways designed so that the setting sun would cast a serpent of shadow slithering down its side on the equinoxes. In these acts, the practical and the spiritual were one and the same. To achieve such perfection required an advanced understanding of measurement and surveying. The consistent angles, the flawless alignments over vast distances, all of it demanded standardized units and incredibly accurate techniques. The Greek Parthenon stands as another masterwork of this philosophy. Its columns swell slightly in the middle to correct for optical illusion, and its entire layout is a play on harmonious proportions, creating a sense of balanced beauty that feels instinctively right. This pursuit was about more than aesthetics. It was about constructing a microcosm of a divinely ordered universe. How many of our own modern buildings, for all their technical prowess, strive for this same deep, resonant harmony? The legacy of these sacred measures is found not in ruins, but in the enduring human desire to build meaning into our world. A royal cubit rod, carved from black granite and marked with precise divisions, was far more than a simple ruler. It was a physical extension of the pharaoh's authority, a guarantee that a temple wall in Thebes would match the blueprint drawn up in Memphis. This shift from the personal cubit of a single farmer to a state-enforced standard was a revolution in human cooperation. In Babylon, the shekel was not merely a weight for silver. It was the foundation of contract law, ensuring a fair measure of grain for a fixed amount of metal. The Roman mile, 1,000 paces of a legionary, became the rhythmic beat that measured the expansion of an empire, allowing engineers to plan roads and aqueducts that spanned continents with a shared language of distance. These units were deeply rooted in the tangible world, the foot, the handful, the day's walk for an ox, making them intuitive for daily life. Yet this very strength was also a profound limitation. A Greek stadium, the length of the racecourse at Olympia, might be 600 of one city's feet, but the next city over had a slightly different foot. This meant that Eratosthenes' stunning calculation of the Earth's size was based on a unit that was not universally fixed, a subtle variable woven into his grand result. The success of monumental projects like the Roman aqueducts, which required a consistent, gentle slope for water to flow for miles, is a testament to the power of this early standardization. Teams of workers using simple levels and calibrated measuring rods could achieve gradients so precise they still inspire engineers today. This drive for consistency was about more than engineering marvels. It was about fairness in taxation and trust in commerce. It makes you wonder, in our own world of global trade and digital communication, how much do we rely on the silent, invisible network of agreed-upon standards, from the definition of a second to the voltage in our walls? This gradual, hard-won journey from local custom to universal system was a quiet prerequisite for every scientific discovery that was to follow. A Persian caravan master would balance his scales not with a single standard weight, but with a unit known as the seri, a measure born from the practical needs of the long road. Along the sprawling Silk Road, caravanserais were not just rest stops, they were vibrant hubs of intellectual commerce. In these bustling courtyards, a merchant from Damascus might show a Chinese counterpart his astrolabe, while an Indian scholar demonstrated the startling efficiency of a new numeral system that included a symbol for nothing, the concept of zero. This was not merely the trade of silk and spices, but a silent, profound exchange of the very tools for understanding the world. The abacus, in its various forms, traveled these routes, turning complex calculations into a tactile, swift process accessible to traders of any language. Arab scholars, acting as the great synthesizers of the age, absorbed the geometric proofs of the Greeks and the revolutionary numerals from India, weaving them into a new, powerful mathematical language. This knowledge, preserved and expanded in libraries from Baghdad to Cordoba, would later cross into medieval Europe, providing the computational foundation for the scientific renaissance that would reshape the continent. The caravanserai itself was a testament to this collaboration, a standardized weight that represented an average, a compromise between the differing measures of many lands, creating a common language for fairness across empires. In the spice trade, Portuguese and Arab navigators slowly pieced together more accurate portolan charts, maps dense with room lines that reflected accumulated, hard-won experience from countless voyages. These charts were state secrets, yet their very existence was a product of shared, often unwilling, knowledge transfer across cultures. Each successful journey reduced the risk for all who followed, proving that the advancement of measurement was, and always has been, a collective human endeavor. In our own era of instant global communication and international research teams, does this ancient lesson of the caravanserai hold a key to solving the complex, planetary-scale challenges we face today? A monk's quill traces the edge of a vast parchment circle, not charting coastlines but sketching the story of salvation itself. In the great Hereford Mappa Mundi, the world is a divine diagram, with Jerusalem seated at its heart like the pupil of God's eye. Rivers flow from paradise at the top, while the three known continents are divided among the sons of Noah. This was not a map for sailing, it was a sermon in ink and vellum, designed to guide a soul toward virtue, not a traveler to a physical destination. Along its borders, fantastical beings whisper of lands beyond human understanding, from the Cyapods who shaded themselves with a single giant foot to the Griffons guarding gold in the east. Yet woven into this rich tapestry of belief are threads of hard-won classical knowledge, preserved when much of it was lost. The map incorporates the geographical framework of the Roman scholar Ptolemy, a reminder that even in an age of faith, the empirical world was pressing in. These Mappae Mundi were acts of devotion where measurement was not about calculating distance, but about understanding mankind's place within a sacred hierarchy. The size of a city on the map reflected its spiritual importance, not its population or physical area. Can you feel the weight of that different purpose, where knowing the world meant knowing its moral story? These magnificent creations were slowly infiltrated by the reports of merchants and pilgrims, their margins annotated with notes of real ports and mountain passes. This slow, quiet collision between a symbolic universe and the stubborn facts of travel would eventually strain the parchment to its breaking point, creating a tension that could only be resolved by a new way of seeing. The legacy of these spiritual guides was not their accuracy, but their enduring power to frame the very question of what a map is for, a question the Renaissance would answer with a decisive turn back to the observable Earth. A dusty manuscript, long forgotten in a monastery library, held a key to a forgotten world. When a 15th century scholar in Florence first laid eyes on Ptolemy's Geographia, it was like a thunderclap. Here was a 2nd century Greek thinker describing the entire known world through a grid of latitude and longitude, a coordinate system that could precisely locate any place on a spherical Earth. This rediscovery ignited a firestorm in the European mind. Humanist scholars, fueled by a new passion for classical learning, feverishly translated not only Greek texts but the sophisticated Arabic commentaries that had preserved and expanded upon this knowledge for centuries. The result was a revolution in seeing. The astrolabe was refined into an instrument of breathtaking precision, and the invention of the telescope turned the heavens from a mystical tapestry into a measurable frontier. In the notebooks of Leonardo da Vinci, this fusion of art and science reached its zenith. His meticulous studies of human proportion and linear perspective were not just for painting, they were exercises in understanding the geometric principles that could render a city plan or a map with stunning accuracy and realism. This was a rebirth of the very idea that the world could be rationally measured and beautifully represented. On the rolling decks of caravels, this intellectual fervor met practical necessity. Portolan charts, no longer drawn as spiritual allegories, became dense webs of room lines radiating from compass roses, each line a direct sailing course based on the accumulated, hard-won experience of countless mariners. These maps were tools of empire and trade, and their increasing accuracy shrank the perceived dangers of the open ocean. What is it in the human spirit that compels us to periodically unearth the wisdom of our ancestors, to dust it off and see it with new eyes? This great reawakening did not just look back, it propelled explorers across uncharted seas, expanding the measurable world beyond the edges of the old maps and into a vast, unknown hemisphere. Ferdinand Magellan's crew, skeletal and weathered, pointed a simple wooden cross staff toward the punishing sun. Each measurement of its altitude was a defiant act of faith in a geometric truth, a belief that the endless horizon was not a precipice but a continuous curve. Their epic circumnavigation was a brutal, living experiment in global measurement, proving with tragic cost that the world was not only round but interconnected. Out on the featureless blue, these explorers wielded a fragile toolkit against the unknown. To find their latitude, they used the cross staff and its successor, the backstaff, which allowed them to sight the sun without blinding themselves. But latitude was only half the puzzle. Longitude, the east-west position, remained a ghost in the machine, a problem that would confound navigators for centuries. They attempted lunar distance calculations, a complex method of measuring the moon's separation from certain stars, but the math was arduous and the required tables often flawed. Timekeeping was their greatest weakness. Sand trickling through an hourglass marked the hours, but rolling decks and changing conditions made these measures unreliable. A captain's best guess, his dead reckoning, could accumulate errors for weeks, leading to terrifying miscalculations where a promised coastline was nowhere to be seen, and supplies dwindled in a watery void. It was this very peril that spurred the Spanish and Portuguese crowns to establish formal schools of navigation. In these classrooms, pilots pored over constantly revised tables and learned the meticulous use of instruments, slowly forging a new class of professional navigator whose charts were based on collective experience rather than rumor. The greatest triumph of these arduous voyages was not merely the claiming of new lands, but the quiet burial of ancient fears. They sailed directly through the domains of sea monsters and over the theoretical edge of the world, replacing mythological terror with a hard-won, empirical confidence. What does it mean that humanity's greatest expansions have so often been fueled by the courage to sail into absolute uncertainty? This relentless push across the oceans created an unavoidable crisis, a desperate need to solve the single greatest puzzle of navigation, the mystery of longitude. The Scilly naval disaster of 1707 was a national tragedy, a nightmare of storm and shipwreck that claimed nearly 2,000 lives. The cause was a devastating miscalculation in longitude, a fatal error that finally forced the British government to act. They established the Longitude Board and offered a prize of £20,000, a king's ransom, to anyone who could solve the greatest scientific puzzle of the age. The challenge was deceptively simple in theory. Since the Earth rotates 360 degrees every 24 hours, every single hour of time difference from a known starting point equals 15 degrees of longitude. But knowing this theory was useless without a reliable clock that could keep the time of that home port through months of violent storms, salt spray, and extreme temperature swings. A clock that lost just 10 seconds a day would accumulate an error of over 25 miles in a single month, enough to steer a ship directly into a deadly coastline. The best scientific minds of the era pursued celestial solutions. Galileo had proposed using the moons of Jupiter as a celestial clock, but trying to focus a telescope on a tiny planetary disk from the deck of a heaving ship was a practical impossibility. Others tried to chart the moon's rapid movement against the background stars, a method called lunar distance, but the complex calculations required hours of work and flawless tables, a task far beyond the average ship's navigator. The idea of using magnetic variation, the difference between magnetic and true north, also proved unreliable as the Earth's magnetic field shifted in ways no one could yet predict. The solution would not come from observing the heavens, but from the quiet, persistent work of a humble English carpenter and self-taught clockmaker named John Harrison. He dedicated his life to building a machine that could conquer the ocean's chaos, a marine chronometer of such incredible precision it could maintain accurate time over a long voyage. His story is one of brilliant innovation and stubborn perseverance against an establishment skeptical of a mere craftsman. He built a series of clocks, each one more refined than the last, using revolutionary materials like anti-friction wood and self-lubricating brass to counteract the effects of temperature and motion. His final masterpiece, known as H4, was a large, beautiful watch that looked more like a piece of jewelry than a nautical instrument, yet it performed flawlessly on a grueling test voyage to the Caribbean. Harrison's chronometer was the definitive answer, but it was the culmination of centuries of incremental progress by countless unknown astronomers, mathematicians, and metalworkers. What does this decades-long struggle reveal about the nature of discovery? It reminds us that great leaps in science are rarely a single moment of genius, but more often a slow, collective climb, where each failed attempt lays a stone for the ultimate path to success. This hard-won union of time and space did not just save ships, it shrank the world, transforming global navigation from a dangerous gamble into a precise science and setting the stage for the next great leap in our journey to measure everything. A quipu, a cascade of knotted cords, looks nothing like a map or a ledger. Yet in the hands of an Inca administrator, this intricate textile was a dense record of information, encoding everything from grain stores to the dimensions of a mountain road. Each knot's position and style represented a number, and the colors of the cords signified the subject being counted. This was a civilization that mastered one of the world's most challenging terrains without a system of writing as we know it, choosing instead to weave their data into a tangible, portable format. Their entire empire, connected by a vast network of roads, was managed through these knotted strings, a testament to a uniquely tactile form of mathematics. Far across the Pacific, Maori navigators did not measure the sea in miles, but in Wakapapa, the genealogical star paths that connected them to their ancestors and their destination. The journey itself was a living narrative, with each star and current holding a name and a story, making the ocean not an empty space to be crossed, but a known and storied realm. Similarly, many Native American tribes defined their territories through relationships with natural landmarks. A treaty boundary might be described as the land from a certain river to a particular mountain peak. These were not abstract coordinates, but measurements embedded in a living, breathing landscape. Can a unit of distance be found in the memory of a song or the silhouette of a hill? This profound connection between measurement and meaning ensured that knowledge was not just recorded, but felt and remembered, passed down through generations by elders and specialists. This wisdom often carried an inherent ethic of sustainability. In Australia, Aboriginal communities practiced fire stick farming, a sophisticated form of land management that required an intimate understanding of seasonal cycles and plant behavior. The timing and placement of these controlled burns were a precise science, measured not by the calendar alone, but by the flowering of specific plants and the behavior of animals, ensuring the health of the ecosystem for generations to come. These systems challenge our very definition of what it means to measure. They remind us that quantification does not have to mean detachment, that a number can hold a story, and a boundary can be a relationship. In an age of planetary environmental challenges, what profound insights might we gain by learning to measure the world not just with satellites and sensors, but with the deep, contextual wisdom of those who have long understood the art of living in balance? Tycho Brahe's Island Observatory became a fortress of data, its walls sheltering decades of meticulous star charts. Night after night, he recorded the precise positions of planets with unprecedented accuracy, creating a treasure trove of celestial observations. Yet it was his assistant, Johannes Kepler, who unlocked their deeper secret. Using Brahe's painstaking records, Kepler discovered that planets move in ellipses, not perfect circles, a revolutionary idea that redefined our solar system's architecture. This astronomical breakthrough subtly refined our understanding of Earth's own motion and position in the cosmos, proving that the laws governing the heavens were intimately connected to our own world. Long before telescopes, this synergy was already shaping human geography. The great stone circles like Stonehenge were not just temples, they were massive calendars aligned to solstices and eclipses, events that marked time and territory with celestial certainty. A solar eclipse could reset a king's reign or confirm a boundary treaty, its shadow falling across the land as a divine marker. This deep reliance on the sky led to one of history's most practical reforms, the Gregorian calendar. By the 16th century, the older Julian calendar had drifted 10 days out of sync with the seasons, confusing farmers and navigators alike. Pope Gregory's astronomers proposed skipping those days and refining the leap year rule, a correction that brought human time back into harmony with the solar year. This recalibration was vital for agriculture and for sailing, as it ensured seasonal star charts remained reliable guides across the ocean. With this stable celestial framework, cartographers could finally project the spherical Earth onto a flat sheet in a consistent way. Gerardus Mercator's famous world map used a mathematical grid that kept compass bearings straight, a life-saving innovation for any sailor plotting a long course. His projection turned the complex curve of the planet into a functional tool, allowing a navigator to draw a straight line from Lisbon to the Caribbean and follow it with confidence. What cosmic events, from the predictable eclipse to the startling comet, first compelled our ancestors to trust the sky as their ultimate guide? This celestial partnership laid the essential groundwork for a global grid of latitude and longitude, a system that would eventually allow us to pinpoint any location on Earth with a set of numbers derived from the stars. Ptolemy's Geographia was a universe in ink, a sprawling atlas of the entire known world laid out on a mathematical grid. In the great library of Alexandria, scholars would have pored over his lists of latitudes and longitudes for thousands of cities, mountains, and rivers. He did not just draw coastlines, he gave them a precise address on the globe, introducing the very idea of a coordinate system that could locate any place with numbers. This was a revolutionary shift from vague descriptions to a structured, quantifiable framework. His work also tackled the fundamental problem of cartography, how to represent the curved surface of the Earth on a flat sheet of parchment. He proposed several map projections, geometric methods for translating the sphere's features onto a plane, a concept that would underpin map-making for centuries to come. For over 1,000 years, his Geographia served as the ultimate geographical authority, a blueprint copied and revered by both Islamic scholars in Baghdad and monks in medieval Europe. Yet this brilliant system was built on a critical flaw, an underestimation of the Earth's true size. Ptolemy's circumference was significantly smaller than the figure Eratosthenes had calculated centuries earlier. This miscalculation had dramatic consequences, most notably his depiction of the Indian Ocean as a landlocked sea, with a vast, unknown southern continent enclosing it. You can almost feel the intellectual tension, a mind of immense systematic power working with incomplete data. So how did such a profound error ultimately drive progress? Because his framework was so precise, its mistakes were testable. When later explorers and astronomers gathered new information, they could pinpoint exactly where Ptolemy's world diverged from reality. His enclosed Indian Ocean, for instance, became a tantalizing question mark. Was it truly landlocked, or was there an open passage? This very uncertainty may have helped fuel the age of exploration, as navigators sought to confirm or correct the ancient master's map. The rediscovery of his texts during the Renaissance was like finding a lost instruction manual for the world. Cartographers like Gerardus Mercator did not simply copy Ptolemy. They used his systematic methods as a starting point, adapting his projections and coordinates to accommodate the flood of new discoveries from across the Atlantic. Ptolemy's true legacy, then, is not the accuracy of his maps but the power of his approach. He demonstrated that even an imperfect framework is better than no framework at all, because it gives collective inquiry a common language and a clear direction. What flawed blueprint of our own time might future generations use as a foundation for their own great leap forward? A golden city shimmered not on any map, but in the desperate hopes of European adventurers. The legend of El Dorado drove conquistadors into the unmapped heart of South America, their minds fixed on a mirage of impossible wealth. They followed real rivers and scaled actual mountains, yet their quest was guided by a fantasy, a geographical phantom that led them to measure distances not in leagues but in promises. These journeys, fueled by greed and wonder, often ended in hardship, as the tools and maps they brought from Europe proved useless against the vast, unforgiving scale of the continent. The search for mythical places like the Fountain of Youth or the northern paradise of Hyperborea created a powerful distortion in early cartography, where the line between observed fact and cherished story was dangerously blurred. Yet within this confusion lay a strange paradox. The relentless hunt for the mythical Christian king Prester John, for instance, sent missionaries and mapmakers deep into Africa, forcing them to document the true sources of the Nile with a detail that would never have been attempted for mere trade. Fantasy became the unlikely engine of factual discovery, pushing the edges of the known world outward through a blend of delusion and determination. This reveals that exploration has always been driven by a dual compass, one needle pointing to the cold stars of empirical data, the other swinging wildly toward the magnetic pull of human dreams. What modern legends, like the promise of ancient oceans on Mars or mysterious creatures in the deep abyss, now draw our probes and submersibles into the unknown? This timeless interplay between the map we can draw and the story we need to believe eventually demanded a new object, one that could hold both the measured sphere of the Earth and the lingering ghosts of its unexplored corners, the first terrestrial globe. Martin Behaim's Erdapfel, or Earth Apple from 1492, is a world frozen in time, a beautiful sphere of painted parchment stretched over a clay core that captures the very moment before everything changed. This globe shows Europe, Africa, and Asia, but the vast space where the Americas should be is empty ocean, sprinkled with the speculative islands of medieval legend. It was a bold declaration of the Earth's roundness, built on the latest Portuguese voyages down the African coast, yet completely unaware of the continents waiting just beyond its western edge. To hold such an object was to hold the known universe in your hands, a powerful, tangible confirmation of a spherical world that a flat map could never provide. These early globes, painstakingly crafted from wood, metal, and engraved paper, were not just decorative curiosities. They were practical tools for scholars and ambitious merchants, allowing them to trace great circle routes, the shortest paths between 2 points on our planet's curved surface. This three-dimensional perspective made complex navigation concepts suddenly intuitive. Yet these models were also filled with confident guesses, like the enormous, hypothetical southern continent of Terra Australis, a landmass cartographers were certain must exist to balance the planet's northern land. Each new voyage returned with corrections, forcing globe makers to painstakingly update their creations, a slow, physical process of refining the world's image. The creation of a globe was a fusion of disciplines. Artists meticulously engraved coastlines onto gauze, the strips of paper that would be carefully pasted onto the sphere, while scientists checked the placement of each latitude line. The result was an object that was both a scientific instrument and a work of art, a centerpiece for a wealthy patron's library that also held the functional keys to global trade routes. There is a profound difference between looking at a flat map and holding a globe in your palms. One presents the world as a diagram to be analyzed, while the other offers a small, fragile planet to be turned and explored, making our interconnectedness immediately felt. This shift to thinking in 3 dimensions was a quiet revolution, training the human mind to comprehend the true geometry of our home in space, and setting the stage for the mathematical precision that would define the maps of the future. Gerardus Mercator's workshop was a place of quiet calculation, where the impossible problem of the spherical Earth was pressed flat onto paper. His great insight was not to perfectly replicate the world, but to make it navigable. He realized that a sailor's most vital need was to plot a straight line, a constant compass bearing, and follow it across an ocean without endlessly recalculating their course. His projection, a clever mathematical cylinder wrapped around the globe, achieved exactly this. It transformed the confusing curves of the planet into a grid of straight room lines radiating from compass roses, a gift to any mariner staring at a chart in a stormy sea. But this navigational clarity came at a cost. To keep those lines straight, Mercator had to stretch the land masses dramatically as they moved away from the equator. On his map, Greenland appears larger than Africa, though in reality Africa is 14 times larger. This was not an error, but a deliberate trade-off, a sacrifice of size for the sake of direction. This single choice highlights the fundamental truth of all mapmaking, that every projection is a compromise. You cannot flatten the skin of an orange without tearing or stretching it somewhere. Centuries later, the Gaulle-Peters projection emerged as a corrective, prioritizing the accurate relative size of continents to counter the Mercator's distortions. It made a powerful political statement about representation, but in doing so, it stretched continents vertically, altering their familiar shapes. A map is never a neutral document. It is an argument about what is most important to show. Is it the true shape of a coastline for a sailor, or the true size of a continent for a student? The mathematical principles behind these models evolved from Ptolemy's early conic projections to complex algorithms used in modern digital mapping. Each one is designed to minimize distortion for a specific purpose, whether for aerial navigation, satellite imagery, or depicting global climate patterns. The maps that guided European empires were not just tools of navigation, but instruments of power. An accurate chart of a coastline or a trade wind was a military and commercial secret, directly influencing the flow of wealth and the fate of continents. This legacy forces us to ask a difficult question. When we choose a map for a classroom wall, what story are we unconsciously telling about the world? Are we prioritizing the navigational logic of the past or a faithful representation of geographical equity in the present? The creation of these increasingly precise models depended entirely on a parallel revolution, the development of instruments capable of capturing the world with ever greater fidelity. A Roman surveyor plants his groma in the dusty soil, its 4 weighted plumb lines hanging perfectly still. This elegantly simple cross of wood was the bedrock of imperial infrastructure, allowing engineers to cite perfectly straight lines for roads that would stretch for hundreds of miles and aqueducts that carried water on a gentle, unerring slope. The precision was almost spiritual, a human-made straightness imposed upon the chaotic curves of the natural world. Over the centuries, this foundational tool evolved into something far more versatile. The theodolite, with its finely engraved circles and telescopic sights, could measure both horizontal and vertical angles with breathtaking accuracy. This transformed land surveying from a matter of straight lines into a three-dimensional art. A single surveyor on a hilltop could now map an entire valley, calculating the heights of distant peaks and the depths of river gorges without ever setting foot in them. This new precision became the language of law and commerce, settling boundary disputes with geometric certainty and creating the detailed land registries that funded empires through fair taxation. Far to the east, Chinese engineers developed a different kind of marvel, the south-pointing chariot. This complex gear-driven vehicle used differential mechanics to ensure that a figure on its top always pointed south, no matter which way the chariot turned. It was a mechanical compass, a triumph of craftsmanship that maintained direction long before the magnetic needle was commonplace. Meanwhile, in the observatories of the Islamic world, scholars were refining the quadrant, perfecting its curved scale to measure the altitude of stars with such fidelity that it could be used for both mapping the heavens and surveying the earth. These instruments were not mass-produced, they were born from the hands of master artisans who understood the soul of brass and wood as deeply as they understood the theorems of geometry. Each device was a unique fusion of art and science, its engraved scales a work of beauty that also served a rigorous computational purpose. So how did a finely crafted theodolite build more trust than a farmer's footstep? Because its measurements were repeatable and verifiable. Two surveyors using the same calibrated instrument on different days would arrive at the same result, creating an objective reality that everyone, from neighboring farmers to royal tax collectors, could agree upon. This growing trust in measured data was the silent engine behind the first accurate national maps, turning the personal knowledge of the land into a shared, dependable fact. This relentless refinement of the surveyor's toolkit was quietly building the framework for a new kind of power, one that would soon seek to measure not just fields and forests, but the very arc of the planet itself. The Cassini family transformed the French countryside into a geometric masterpiece of sightlines and measured angles. For 4 generations, they directed a monumental effort, the first complete triangulation of an entire nation. Teams of surveyors climbed church steeples and hilltops, using massive theodolites to measure angles between points, creating a vast, unshakable web of triangles that stretched across France. This was no longer the tentative chart of an explorer, but the precise blueprint of a state, a map so accurate it set a new global standard. Across the Channel, the British Ordnance Survey embarked on a similar mission, driven by the need to secure the nation after the Jacobite rebellions. Their detailed charts of the Scottish Highlands turned a mysterious, rebellious territory into a known and manageable landscape. In the young United States, the Lewis and Clark expedition mapped a continent's interior, systematically documenting rivers, mountains, and resources, transforming the Louisiana Purchase from a vague claim on paper into a tangible national asset. These projects required armies of cartographers and mathematicians, their work fueled by military necessity and economic ambition. The resulting maps did more than just show where things were, they actively shaped the concept of the nation itself. A clearly defined border reduced disputes with neighboring powers, while detailed interior maps allowed for the rational planning of canals and, later, railway networks that bound the country together with iron rails. Can a map help you feel a sense of belonging to a place you have never even visited? This systematic capture of the land, this transformation of soil into data, was the final piece needed to unite the measurement of space with the mastery of time, creating the comprehensive geographic systems that define our modern world. John Harrison's H4 chronometer endured the violent lurch of the Atlantic. Its intricate springs and counterweights a tiny, ticking fortress against the chaos of the sea. This was the final piece of the puzzle. For the first time in history, a ship could carry the precise time of its home port anywhere on the planet. That single, steady tick transformed the abstract geometry of the globe into a practical reality. By comparing the local time determined by the sun with the time shown on the chronometer, a navigator could calculate their east-west position, their longitude with certainty. The marriage of this portable time with the ancient art of celestial navigation gave birth to a true global coordinate system. Every bay, every mountain, every city could now be assigned a unique numerical address defined by its latitude and longitude. This was more than a cartographic revolution. It was a new way of organizing human activity. With the world pinned to a precise grid, synchronized schedules became possible. The telegraph could transmit messages along routes measured in both miles and minutes, and railway companies could publish timetables that passengers could actually trust. This newfound precision inevitably collided with the sun's own schedule. For centuries, noon was a local event when the sun reached its highest point in your specific town. But a train traveling east or west would pass through dozens of these local noons, making a standardized schedule impossible. The solution was to slice the world into 24 neat time zones, each 1 hour apart. Suddenly, the planet operated on a coherent temporal grid, where 8 a.m. in London meant a predictable time for opening a stock exchange in New York or dispatching a ship from Bombay. How does our perception of distance change when we can measure it in time? We speak of a place being a 6-hour flight away, collapsing space into a duration. This profound unification of time and space, forged in the rolling cabins of sailing ships, did not just make travel safer. It wired the world for the synchronized, instantaneous communication that would define the century to come. A Polynesian navigator, feeling the subtle tug of a current shift or noting the specific flight path of a seabird, was processing data in a way our most advanced sensors still struggle to replicate. This was not measurement in isolation, but a deep, contextual reading of a living system. Modern ecologists now study these ancient wayfinding techniques with profound respect, seeing in them a model for sustainable interaction with our environment. The navigator's success depended on the health of the entire ecosystem, from the stars above to the life within the sea, a holistic understanding that we are urgently relearning today. These ancient arts of measurement stand as a powerful reminder that our greatest innovations often blossom from constraint. Faced with the immensity of the ocean or the curve of the earth, our ancestors used simple sticks, knotted ropes, and their own keen observation to achieve insights of staggering profundity. They prove that diverse cultural perspectives are not just historical footnotes, but vital chapters in the story of human problem solving. The Greek geometer, the Inca quipu keeper, and the Persian astronomer each approached the challenge of quantification from a unique angle, their collective wisdom creating a richer, more complete picture of our world. At the heart of all these methods lie core values we risk overshadowing in our digital age: patience, deep observation, and interdisciplinary thinking. They force us to slow down, to truly see the patterns in the shadows and the stories in the stars, blending astronomy with storytelling and geometry with art. In an era of instant GPS and overwhelming data streams, this historical journey offers a crucial counterbalance, a lesson in humility and resilience. Our modern world of precise coordinates and global communication rests entirely on the foundational work of those who measured the Earth with little more than their own intellect and perseverance. So as we face our own monumental challenges, from navigating the complexities of climate change to charting a course for Mars, we might ask ourselves, what timeless principles can we carry forward? The answer lies not in abandoning our technology, but in complementing it with the ancient wisdom of listening to the world, of understanding that true measurement is as much about meaning as it is about numbers. This invaluable heritage is not a relic to be stored in a museum, but a living compass guiding us toward a more thoughtful and connected future. Our journey across the ages reveals a profound truth that the human drive to measure our world is as ancient as civilization itself. We have walked from the sunlit well in Alexandria to the vast star paths of the Pacific, seeing how shadows, sticks, and stories unlock the planet's deepest secrets long before the first satellite ever blinked in the night. This was not a story of superior technology, but of superior imagination, a creative fusion where mythology gave meaning to the unknown, mathematics provided its logical skeleton, and patient observation filled in the living details. The stunning precision achieved by an Eratosthenes or an Al-Biruni proves that accuracy is not a modern privilege, but a human potential. These historical endeavors did more than just map coastlines. They wove the first threads of global connection, fostering scientific progress and cultural exchange that would eventually bind all of humanity into a single, shared geographical story. The true legacy of these lost arts is not found in any single map or number, but in the enduring spirit of curiosity they represent. So the next time you glance at a map on your screen, take a moment to consider the epic journey of discovery it represents. Why not try your own hand at this ancient art? On the next clear day, plant a stick in the ground and track its shadow, using nothing but the sun and your own reasoning to uncover a small piece of the cosmic puzzle. We would love to hear which method from our journey amazed you the most. Share your thoughts in the comments below, and if you enjoyed this exploration, subscribe for more voyages into the wonders of our shared past. Remember, the greatest discoveries often begin with a single, simple question asked beneath an open sky.